Uh, Welcome to the micro engineering course. Today we will discuss the modes in a rectangular waveguide. As we have mentioned earlier, that a rectangular waveguide it is act as a high pass filter and it operating in a specific band of a frequency. And then size of that rectangular waveguide, that is height and width of this rectangular waveguide. So it is depending upon what will be the operating frequency. You can say that it is nothing but your waveguide. Now for the given waveguide, this width and the height, it is depending upon that the frequency there, or we can say that it is depending upon that lambda. So all these factors are depending upon that frequency and the lambda. So that's why we need to know about what is the operating frequency of this waveguide and what is the cutoff frequency of this waveguide. So cutoff frequency means what? A lowest frequency that is to be propagating through this waveguide. So to obtain the equation of a cutoff frequency, so we should know that some excitation component, that is your electric field component and a magnetic field component. Now generally if you see rectangular waveguide, so for the guide along with this width side and this is about height, we say here I supposed to write here this one is width, everyone know that, and this one is about the height of the waveguide, and this one is about the length doesn't matter, length is depending upon that in which applications we are using this rectangular waveguide. Now for this width, if you see that there are some electric field component and magnetic field components are there, and if you see the excitation of those field components, so how your electric field component and magnetic field components are looks like inside the waveguide. Now generally the field distributions for the rectangular waveguide are that is along with this height or along with this width there, and we can say that here the field is distributed inside the waveguide. That distribution of field is just supposed to be say that is about a half field distribution, or we can say that half sign distribution, or we can say that a full sign wave distribution. Okay, that distributions is recorded depending upon that what is the width and whether it is half field distribution, so it is mode 1. Full sign distribution, then it will be a mode 2. Okay, likewise that modes are depending upon that what is the field distribution. Now we just remember that this particular portion that is about the width, and we say that here we have the maximum intensity of the field component at this point, maximum intensity there. And now we can say that this one is about your field distribution. Suppose I am going to draw a half sine wave, okay, half sine wave, and this is about a half sine distributions of a electric field. Your electric field component always perpendicular to the whatever the width, and this is about a, we say that a half, okay, half field here, or we can say that half sine E field distribution. Okay, so you can write that half sine E field distribution. Now then we say that we have the rectangular waveguide. Then what about the field distributions for this magnetic field? Generally, we say that for the rectangular waveguide, if it is a rectangular like structure, it is about supposed to be a rectangular cut section you supposed to be consider here. And then in this case, we have a Transverse electric field propagation, this is about your A field is likewise. This is about your TE propagation. And a transverse magnetic propagation, that is about a TM propagation. So it is just like a area field distribution is likewise. Now if we consider here, electric field is vertical and then magnetic field will be a horizontal here. So we again go to define a field distributions component for the magnetic field. In that case, that magnetic field component are, it is about a vertical in nature. Okay, magnetic field components are vertical in nature. Likewise, we have the half field distributions here for the half sign H field distributions here. So this is about a H field distribution. So this one is about a half sign, then a full sign distributions. According to that, we say that a modes will be there. For example, I suppose to be consider that we have the rectangular waveguide here. We have the another rectangular waveguide. I suppose to be considered here. Okay, I'll draw this 3 1 so that you will be easily understand that how that field distribution is going on here. Now I say that we have the half field distribution, so intensity will be maximum at the center. This is about your electric field component. Then we supposed to be talk about that there is a full sine wave distribution. Okay, so we can say that after this particular half of the portion, okay, so we can say that up to this we have a positive field intensity here, but from this we can say that this will be a downward one. Okay, alternately it changes. This is about, we can say, a full sine distribution. Now I suppose to be consider that we have the 1.5 field distribution. Then this one is about a positive here, then upward, then a downward. Okay, likewise. So this one is about a half. Okay, so we can say that 1.5 sine E field distribution. This one is about a full sine E field distribution, and this one is about, we can say, a half sine field distribution. So similarly, we have the magnetic field distributions. Okay, so magnetic field distributions will be just like likewise here, whether it will be half field distributions or a full half or a full sine distributions or 1 and 1.5 distribution. Now, based on these distributions, we say that a number of modes. If now here is a 1/2 distribution, that is about one mode, two here, that is called as two. Okay, three here, because three halves are there, two halves are there, so that's why it is called as a three. So modes distributions we will see here for the electric field distributions as well as for the magnetic field distribution. Now, how that modes are distributed? For that purpose, we should know that what are the field components there, electric field components and a magnetic field components and their nature for the distributions of the electric field and a magnetic field there. Okay. So earlier we have seen that Maxwell's expression, that is a del cross E, del is a vector 1 is equal to minus dou B bar by dou T, or we can say that minus j omega mu H. Then a del cross H here is equal to, now there are the two components, that is displacement current density and a conduction current density. This one is the conduction, this one is about the displacement current. So we can say here, so instead of that sigma E, we can write here only the J. Okay, so J is equal to, we can say that sigma E here plus, we can say that J omega epsilon. Now these two components. Now if you take a del cross E or del cross E, that is a vector here. So del square E, okay. So it is nothing but what? A j omega mu into sigma plus j omega E here. And this one is about a minus A. Okay, so this minus del square E and minus j omega mu. So it is just like a plus here we can write. Del square E is equal to what? We'll get that expression that is about a j omega mu and bracket of sigma plus j omega. Now this is a component, we say it is about your propagation component. Okay, so now when we talk about that expression of wave through this Maxwell's equation, we'll get this constant term. Now we can relate this constant term in a waveguide, and then we need to obtain the field component for a rectangular waveguide in terms of a electric field and a magnetic field there. We use this two Maxwell's equation, and we will obtain that using this Maxwell's equation. If you solve this Maxwell's equation here, okay, if you solve this Maxwell's equation here using this del cross E, del cross B here, sorry, del cross E and del cross EH here. So simple, I suppose to be consider that if one of the equation that is about a del cross E here, that is equal to, we need to talk about that a propagation constant term, and then for this given particular propagation constant term, we supposed to be consider that factor of what, that is a unit vector here. We supposed to say that ax unit vector, ay unit vector, az unit vector. Then this will be a dou by dou x, dou by dou y, and a dou by dou z. Then we have this component of what? Ex, Ey, and Ez here. Now if you solve this equation del cross E, we know that del cross E is equal to minus j omega mu h. Okay, this one. And if you put that minus j omega mu h here, and if you solve for the different component, we'll get the component of, or we'll get the equation in terms of a electric field component Ex, Ey, Ez. Similarly, if you solve with a del cross H, and then we'll get the component in terms of a magnetic field. Okay, so alternately we are getting the component in terms of a electric field, we are getting the in terms of a magnetic field. A relation here, it is saying that electric field is dependent on the magnetic field component. Magnetic field is dependent on the electric field component. Now these terms we supposed to be used to obtain the equations in terms of electric field and a magnetic field. I directly write the equations for this rectangular waveguide, and through this we say that we have the field component we supposed to be considered, that is Ex for the rectangular waveguide is equal to minus gamma by kc square dou Ez by dou x minus j omega mu kc square dou hz by dou y. Then similarly we have the ey component minus gamma kc square dou ez by dou y plus j omega mu kc square dou hz by dou x here. Then hx component j omega epsilon by kc square into dou ez by dou y minus gamma kc square dou hz by dou x. Then hy minus j omega epsilon kc square into dou ez by dou x minus gamma kc square dou hz by dou y. Now this one is, these are the expression in terms of electric field here. These are the expressions. We have the magnetic field term there. Okay, that is about the solutions in terms of electric field and a magnetic field. And this kc square, that is equal to gamma square plus omega square mu epsilon. Because we say that a wave is propagating in the z direction. So earlier we say that our wave equation, we say that e raised to minus gamma z, that is about a forward wave. And this gamma is nothing but what? Alpha plus j beta. We say. And that alpha plus j beta, it is showing that a propagation constant and what is the attenuation of a wave when your wave is propagating in a forward direction. So now from this equation, if you see that we have the component, okay, now we can say that Ex is equal to what? We have the component in terms of Ez and Hz here. Ey again, Ez and Hz. Then we proceed here, Hx, Ez, Hz, Hy, Ez, Hz. Which common thing in all these equations are, we say that wave is propagating, it has the electric field component along with x, y and z. Okay. Similarly, we have the component of x, y and z. But as we say that uniform plane wave, okay, we have seen earlier, and in which your wave is propagating in a z direction. And here we say that supposed to be x and this is supposed to be y. So then we have the electric field vector component here. This one we say it is about a ex now. And we have the magnetic field component. This is supposed to be from this waveform. We say it is about E, Hy component. Electric E and it is about H component. So now common thing is that we say that your wave is propagating in z direction. From this waveform, from this wave, we say that it has a electrical field component in the x direction and magnetic field component in the y direction. This from this diagram we see. But if you talk about this equation e raised to minus gamma z, here we say that wave is propagating in a z direction. But right now we say that from the waveform we say that it has a x, ex and hy component. But if we say that wave is propagating only in a z direction, then we can say that it has either electric field either X or Y component. Okay. Similarly, we say that magnetic field it has either X or Y component. But from this waveform, we can understand electric field only X component and magnetic field only Y component. But the equation is given here, e raised to minus z, gamma z, which your wave is propagating in a z direction. So then we have a combination of component that is, we can say here, electric field has a Ex and a Ey component. Similarly, the magnetic field has a X and a Y component. And wave is propagating in a z direction. So that's why we have this, all the equations of electric field and a magnetic field. We say that Ex, Ey, but other components are in terms of a Ez and a Hz. Your equation of a electric field as well as the magnetic field components, they are with respect to that Z component, because field has a longitudinal component. Okay, we can say that that wave propagating through the rectangular waveguide, it has the longitudinal component. Now, which longitudinal component is there means along with the direction of propagation of wave. Longitudinal component means what? That component is propagating toward the direction of propagation of wave. So we here is supposed to be from this waveform. We say that this waveform is propagating in a rectangular waveguide now. Then we say that it has X component, Y component. But again, one more component that is longitudinal to the direction of propagation, that is about a Z component, is there along with the rectangular waveguide. Now then, which component is present? Whether it is Ez component or Hz component, or whether it has a both the components are there. Okay, now we'll talk about this, and then we say that what are the various. We just remember that we have the field component Ex, Ey, Hx, Hy, and both the cases, all these equations are in terms of a Ez on Hz. Okay, now we supposed to be say that here fact about that your field components are, I just supposed to be, okay, use this one. Okay, so now I'm saying that we have the Ez component is equal to 0 and Hz component is 0. If that both the components are 0, means we can say that both the longitudinal components are 0. When both the longitudinal components are 0, then what type of wave is propagating through the waveguide? Okay, in that case, what happened here? All the if we say that Ez and Hz are 0, then all the field components become 0. Then that 0 component indicates that wave with a component transfer to the direction of propagation. So that's why what we can say that wave is called as a transverse electromagnetic wave. That is, from this we say it is about a TEM wave. Now next, we are supposed to be consider that Ez is not equal to 0. That Ez is not equal to 0, but Hz is equal to 0. Now from this, all the components are not 0. Only that what happened? That there is a possibility of a existence of a wave because all the components are not 0. Only one of the component, this one is not 0 and this one is about a 0. Now according to this equation, all the components are not 0. This indicates that there is a possibility of existence of a wave in the waveguide. Then what wave is propagating? We say that here Ez is not equal to 0, only Hz is equal to 0. So means it has a magnetic field component that is normal to the direction of propagation. This wave is propagating, it has z component is 0, that is longitudinal component. Okay, it is a 0 here. Means your wave has only a magnetic field component, that is about, you can say that is about a electric field, magnetic field component hx and a hy. Both are perpendicular to the direction of propagation of wave. Then in that case, the wave becomes a TM wave. Here, Az is 0. Here is the longitudinal component of Ez is there. But here the wave, it has a field component, that is magnetic field component is perpendicular to the direction of propagation. That's why that wave has a magnetic field component. So that's why we say that Z is equal to 0, there is a TM wave. Next, we supposed to be consider that a Z is equal to 0 and Sz is not 0. Then Ez is equal to 0 means what? Here we say that Ez is equal to 0 means there is a electric field component, longitudinal electric field component is 0, and this wave propagating through the rectangular waveguide, it has a Ex and Ey component. That components are perpendicular to the direction of propagation of wave. But here Hz is not equal to 0 means what? That longitudinal component of magnetic field vector is present. Here longitudinal component is not present. So that's why that wave becomes called as a T mode of a propagation, or you can say that your electric field component, it is a normal to the direction of propagation. So that's why your wave is supposed to be called as a T wave, transverse electromagnetic wave. That is about a T wave. Then another case, if that Z is not 0, even Sz is not 0. Okay, both the things. Ez is not 0, Hz is not 0. Means what it indicates that the field components are non-zero here. Okay, that is along with the, what we can say, along with the direction of propagation of it. Okay, so means what we can say that there is a field existing in the waveguide, but that particular wave is propagating through the guide. It is generally called as a hybrid wave or a mixed wave. It is called as a hybrid wave or a mixed wave. So then that hybrid wave or mixed wave means what? We can say that it has a TE component as well as a TM component. Okay. So means your wave is propagating through the guide. It is a combination of what? TE and a TM that is propagating through the waveguide. So now with this we say that here just important thing is about TM, T, T, TM, T and hybrid. So now this TM wave is it what we can say that a transverse electromagnetic wave, and this TM wave, it will not exist in a rectangular waveguide. So that's why we will not see this TM wave. It is existed in a transmission line. But TM and a T wave, it is this wave is existing in the waveguide. So we'll see or we'll talk about that T mode of a propagation and a TM mode of a propagation. Now using this equation of a Ex, Ey, Hx, Hy, that equations are used to derive the solutions for this wave equation. And through that, we will say that a T wave solution or a TM wave solution. I will take an example of this T and a TM here, and then from this, we supposed to be calculate that what are the field components. So now from this rectangular waveguide, we'll talk about that a T wave or T mode. Okay, T wave or a TM mode. So mostly people are saying T wave or a TM mode of a T mode of a propagation, TM wave or a TM mode of a propagation. Now is there a T wave described because T wave means transverse electric wave is propagating through the waveguide. Transverse means what? Perpendicular. Means your wave component, electric field component are perpendicular to the direction of propagation of wave. So it's transverse. Okay. So in that case, no longitudinal component is propagating. No longitudinal component of electric field is propagating through the guide. So means what? That Ez is equal to 0. T wave means what? No longitudinal component propagating through the guide. So that's why Ez is equal to 0. Then from those equations of Exey, Hxhy, so if you put that Z is equal to 0, then we'll get that Ex is equal to what? Minus j omega mu by Kc square dot dou Hz by dou y. Now that earlier in Ex, Ez component was there. That Ez component is 0. So that's why the term is 0. Only this term is there. This electric field component, that transverse electric field component, can be obtained from the longitudinal component of a magnetic field. Similarly, Ey here is equal to j omega mu by Kc square into dou Hz by dou x. Okay. Then Hx here minus gamma Kc square to dou Hz by dou x. Then Hy is equal to minus gamma Kc square dou Hz by dou y. Now these are about the expressions of electric field Exey in terms of Sz, magnetic field Ehxhy in terms of a Lz. So our aim is about to obtain that the equation of a Hz here. What is the equation of Hz? And from that equation of a Hz, we can obtain that a wave equation. So how to obtain that a equations of a Hz here, because it is about, we can say it is about a transverse magnetic field. So as we know earlier that now we say that Ez is equal to 0. Okay, understood now. Ez is equal to. Then we talk about that wave equation. What is the wave equation? Because our aim is about to obtain the equation in terms of Hz, we need to talk about that del square Hz component is equal to mu epsilon dou square Hz by dou t. Okay, so del square Hz is equal to mu epsilon dou square Hz by dou t square. And we mentioned earlier that field component Hz, y, z, and t. The term Hz is saying that it has a propagation component along with z is equal to Hz of what belongs to x, y here into e raised to minus gamma z e raised to j omega t. Now we solve this one for this del square h. So del square hz, that del is nothing but vector operator. So in that case, we will get the equation of what? Dou square hz by dou x square plus dou square hz by dou y square plus now here dou square by dou z square h. Now this dou square by dou z square, because wave is propagating in a z direction, so directly we can write dou by dou z is nothing but what we can say a gamma here, dou by dou z. So that's why about a gamma square hz, and that del square hz is nothing but what we can say, that is about a minus omega square mu. It is equal to what? Minus omega square mu hz, mu epsilon, mu epsilon. Okay, now that is about it. Now use this equation. So gamma plus omega square here, gamma square plus omega square mu epsilon. If you take these two terms here, add here, it's will be outside here. So this particular term, gamma square plus omega square mu epsilon, that is we say earlier that is about a kc square. Now this is about a kc square, whichever we have written here in this expression kc square, that obtained through this wave equation. Now use this expression and then we can find out the component of hz here. Solve this, solve these equations. Okay, these two equations here. Now we say that some substitution of hz in terms of a constant term, and we solve this particular equation. So after solving that equation, because we will get that equation in terms of a hz here, and then you can use that hz equation to obtain that ex ey hx hy here. Hz is to be obtained, then we will get that ex ey and hx hy component. So that is about the way to obtain that expression for the electric field component and a magnetic field component. Now come to the topic that T wave mode of a propagation here. Now earlier we say that a kc square is equal to gamma square plus omega square mu epsilon. Now this gamma and that kc, if you see that this kc is nothing but what? A component that will provide you the cutoff frequency, or we can say that it will provide you a cutoff number for this rectangular waveguide. This is nothing but a generally we say it is about a eigenvalues, and that can be defined for this rectangular waveguide. There are some limitations, or we can say that about a boundary conditions for this given waveguide. So if you rearrange these terms here, so gamma is equal to alpha plus j beta, we say this gamma, so kc square minus omega square mu epsilon. Get that equation, that kc square minus omega square mu epsilon here. Now this omega square mu epsilon, okay, this term here, that is we supposed to be consider that it is about a k here. Okay, so we supposed to be solve this particular equation to obtain the value of a propagation constants and all, or from this we can find out a component of magnetic field component or a electric field component. Right now we just take example. First of all, we say that omega square mu epsilon. Generally we say that k is equal to what? Omega under root of mu epsilon. So this k square is equal to what? Omega square mu epsilon. Okay, k square is equal to what? Omega square mu epsilon. So from this here, if we take out a common k here, then expression for this gamma is equal to what? Minus k minus term here. So under root of minus 1 is equal to j. That's why we can supposed to be consider that j and a k here. Okay, this is nothing but a jk here. Under root of k, we can say that this term here. Okay, so this kc is minus here. So 1 minus then kc by k here. This is about your expression. So kc is nothing but what? K is omega mu epsilon, and that kc, suppose we say that a kc is equal to what? Omega c under root of a mu epsilon. Okay, so this kc is equal to what? Omega c mu epsilon. If we say right here omega is equal to twice pi f and omega is equal to twice pi f, so this propagation constant expression j k under root of 1 minus k, this will be equation of 1 minus bracket fc by f bracket jk minus fc by f bracket square. Now this propagation constant, we say that gamma is equal to jk 1 minus under root fc by f bracket square. So I'll rewrite here the expression again, or we're supposed to say that propagation constant is equal to what? Jk under root of 1 minus fc by f. Now what do you mean by this fc? Fc is nothing but what? A cutoff frequency, and f is supposed to be a signal frequency that is propagating through the waveguide. Now from this expression of a propagation constant, we can obtain three Ks for the wave propagating in the space there. So now if supposed to be consider that f is greater than the fc, if that signal frequency is greater than the fc, f is greater than the fc, so then what will be your propagation constant? So that propagation constant term, if this f is greater than the fc here, so this becomes a imaginary here. So we can say that wave is propagating in a rectangular waveguide. If f is equal to fc, okay, f is equal to fc, it's 1 minus 1, 0, okay, so that's about 1 minus 1, 0 here. So in that case, gamma is equal to 0, means we say that no wave is propagating through this waveguide here. And another case, if we say that f is smaller than the Fc here. So when f is smaller than the Fc will be here larger. This is minus j here. Okay, so we can say that minus j plus j here. This will be cancelled. So it is nothing but a e raised to that it has only a real term. It has only a real term. So in that case, when it has a real term, then gamma is equal to what? It has only a instead of alpha plus j beta, it has only alpha term, which is attenuation component. So wave is propagating through this guide when signal frequency is less than the cutoff frequency. That wave is attenuated in a rectangular waveguide. Here only the case is that if f is greater than the fc, signal frequency is greater than the cutoff frequency, then wave is propagating through the waveguide. F is equal to fc, no wave is propagating through the guide. F is less than the fc, signal get attenuated through the waveguide. That is called as the evanescent mode. That's all about your transverse electric wave, TE wave here. Now we will discuss other equations in the next lecture. Now from this, we just understand that these three cases